So, before we start, sure any of you saw this? Donated?
Oh, yeah, last week. Everything's fine. Some of the stuff that I need to do.
Alright, mark it down. I go today.
Oh, wait, what? What'd you mark me down for?
Donated blood.
Oh,
Later on, we'll do if you donate, you can get extra credit.
Oh, you see that?
I don't think you need it, but
I'm pretty good.
all right.
And make sure they call me.
Not sure if you guys saw this, but I'd say biology in the news, but parasites in the news.
And the malaria?
It is. It is out in Houston. Not only that, but a 6-year-old boy died. Died from it, and that was probably what triggered the searches, because they start asking. I mean, the common question is, where have you been? And the responses has been, well, out in the yard playing in sprinklers, playing in a splash pad. And they're like, well, what lakes have you been to? What rivers have you been to? And the parents said, we didn't go to those. And I'm sure they were asking, are you sure? Did you forget? Did you go on this weekend? Did you go here? Started naming places, and they're like, no, we went to the splash pad. We went to, we played in our yard. And splash pads aren't that surprising. It's been reported up in Kansas, I believe, Oklahoma. I think Oklahoma. A study that went around to splash pads and detected it in like some of the puddles around the area, but they found it in like the tap water supply coming out of the hose. So this popped up. I saw this. This was on Saturday. That's when it was updated. I think it was Friday or Saturday when I read the story. So yeah, it's issued for Lake Jackson, Freeport, Angleton, Brazoria, Richwood, Oyster Creek, Clute, Rosenberg, Texas. That's a massive area. Normally you think of this as being in ponds, lakes, but it's in the water. It's in the water supply. So they're trying to disinfect the entire water lines. And that means like opening up water lines, making sure all the water lines get cleared out. You have to hope that people actually open up their water and drain the lines. Thought I'd point it out. Parasitology is on track in spring, so there's a plug. All right, so other news. So I got the grades, the exam grades. They are up. I made a new column in Blackboard gradebook that basically adds up part 1 and part 2 of that exam. So all that you're going to do is just add up the scores. So it's out of 70 some points, 75 points maybe. Your grades are up.
I don't know if is there a way to make it so you can go back to your answer? I typed in the wrong number.
Oh.
I couldn't go back.
Yeah, no, that was kind of put in place.
Oh.
So overall, grades were right on track. I believe the average, class average was at like 89%. So that's in line, and no big surprise that the theoretical portion was the lower of the two grades, the parts. Just a couple things on the R stuff. Length. So sample sizes. You can get a sample size. A sample size is essentially how many data points we have in that vector, or how many rows we have in that vector. But probably the easiest one is to use the length function that calculates the length. There's a couple other ways to do it, but that's what we're looking for. I did see a couple people say sum, which if you did sum of your frequencies vector, that works, because when you use the rep function, the times takes that frequencies to basically create that number of rows. So that worked out. But overall, yeah, the R stuff was pretty good. check it out. I'll get the key posted for that exam. I think I released the review on Blackboard, so you can access the theoretical portion and see the questions and what you missed, what the answers were. I believe I've released that. If I did not, then let me know. You access it by clicking on your grades, go to the exam score, and click on the actual score. That'll open up the quiz, or that'll open up the exam. For the R Markdown stuff, I'll make a PDF document as a key and get that posted, so you can look at it. All right, I asked you to do this Bayes theorem. So we have, we'll start with the quad test. Hopefully you did this. So what Bayes theorem is working with conditional probabilities. And the application of it is, if we get a positive test, how likely is it that we are actually positive? And that comes up a lot. Just because you detect something by PCR doesn't necessarily mean that it's there. You kind of have to account for, false positives. You have to account for the likelihood that you can actually detect it, so our sensitivities and so forth. So first up is this quad test. We have 81% sensitivity, 5% false positive rates. All right, if we assume that Down syndrome is, the prevalence is 0.1447%, then what's the likelihood that the child actually has Down syndrome if the test comes back positive? So we're going to work at this first, and then we can kind of talk about this cocaine. Let's start here. Do it again. All right, so remember we have the probability of having a test come back positive is equal to the probability that we actually have our condition times probability that we will test positive given that we have our condition. So given that it applies our conditional probability. Plus we're going to have all of those times where we don't have it, yet we still test positive. So that's our positive. And then what we're asking for, what's the chance that we actually have it, given that we do test positive? And that's going to be all of those times that we have it and we test positive over the number of positive tests that we have. So first up, we have our practice. So this is our quad test. All right. Probability that we have it, so the probability of yes is going to be equal to that 0.1447%. So a pretty small percentage. That's our probability. We have our sensitivity. So this is where it's good to kind of make our table. Where we have our condition as yes or no, and then we have our test. Because it's the test, the probability of getting positive or negative, that's conditional on our underlying condition, whether we have it or we don't. So we said our sensitivity is 81%. Where does that go in our table? Yes, it's positive. 0.81. What is this value? Right? Because again, we sum across the rows. And then we said false positive is 5%. So we don't have it, we test positive, that's a false positive. So we said 5% there, which means this one's 0.95. What is this 0.95?
If they win, it'll be
The specificity. So actually not detecting it when we took those apart, we don't want any cross-reactivity.
How much are they charged?
All right, so we have everything. So first up, what we're going to do is calculate our plus. So probability of getting just a positive test will be equal to our probability that we actually have it times
have it and we test positive, 81%. And then we're going to add times that we don't have it. So we don't have it. We say that this was yes, then probability that we don't have it is 1 minus that value.
I'm gonna work on the videos on it. So, you're not up here, I have a trainer, no problem. Yeah, we'll start watching.
8,553.
A movie or something. Last night we had.
And just try to avoid surprise. All right, so we've got
I don't even remember what he was saying.
3, that's a no, and then we're going to test positive. Those cases, 5% of the time. We have a bunch of no's. All right, overall probability getting a positive test is 5%. 0.05. 0.05. Does that sound about right? All right, so that's our positive. Now we want to know if we do test positive, what's the chance that we actually have it? Well, we already have that part. So that's the time we actually have it. We want to know what proportion of the times we test positive we actually have it. So do this. What did you get? That you get? So if our test comes back positive, what's the probability that we actually have announced? That's not good. So how do we fix it? And at this, you would never run this test. Never run. But we do. How do we fix it? Does everyone get it? No. What this test is going to do is it's going to be recommended when you have a high likelihood of actually having a Down syndrome child. All right. So instead of looking at the overall, what the doctor's going to do is take all the information that they have and assign risk. So at some point, and that's where I have this graph. So they're going to look at the age of the mother. They're going to look at genetic history, family history. They're going to look at measurements of that developing fetus. Right? They're going to do all these things to try to increase this percentage to improve this. So what's on that graph? What's the highest we have? So let's say we change this and say instead of 0.0014, they say we have it so that it's a 50% chance. All right, let's say we have 50%. We've taken all the measurements, we've done everything, looked at risk categories, and we have it set up so that in this mother, they've got a 50-50 chance of having Down syndrome. How does that change results. How does this change our probabilities? Well, first off, it's going to change how many tests actually come back positive. So we're going to have 50%, that's when we actually have it. We've got 81% of those of the time we'll test positive. And then the other 50%, we're going to have false positive. All right, so let's figure out in our new case where we really reduced who gets tested. 143. All right, so now we have 43% of all of our tests will come back positive. And now what is our guess, given that we have a positive test? 0.05, 0.5, over 0.43. Now you can see what has happened. We've really increased the likelihood that the test could be reliable. Very different in terms of accuracy, right? We can look at this test. We can say, well, how accurate is it? Someone may say, well, it's 81%. Not that great, but that's not how we should think about it. We should always think about it as that 81% really depends on these numbers. What's the chance that we actually have it? Or what's the prevalence in our population? All right? So, if we can get this up high, I mean, 50% is pretty good. You might want to go with that test. But if it's only down to, let's say, 20% chance, I'll let you run the numbers, and then you kind of get this value, this percentage. Is the risk worth it? Risk worth knowing? All right? Questions on this? Did you work through the Cozart microplate? So what did you get? Cody? So it's this is our big question. So you get pulled over, cops give you a test. Coming over here to check, see if there's any questions on YouTube. So you get pulled over. They're like, hey, have you been drinking? And you're like, no, officer, I have not been drinking. And I said, I don't believe you, get out. So they run the full battery on you and you pass with flying colors and they say, I still think you're under something. So they pull out this kit. And you know it's a problem when they pull out the kit and the plastic starts to deteriorate because it's been in the back of their squad car the entire time, right? And you're like, open up, and they swab you, and it's like, haha, you're positive, and they arrest you, and it's like, hey, I hit my quota for the day, right? We know how that is. Maybe it's true, maybe it's not. Who knows? All right, so he comes back and you appear before the judge, and the judge is like, how do you plead? Like, well, I'm not guilty. Like, well, the test comes back positive, and you're like, okay, officer, let me tell you something. You tested positive. What's the chance that you were actually on cocaine? What'd you get?
My question to you.
Yep.
I don't know if I did it right, but I got positive time.
All right, let's do question 1. What's it? So 89% chance that you're not on it, right?
Yeah.
And that assumes perfect application. Right? That assumes that everything is correct. That user error didn't factor in, which is a big part of it. So we had 0.89. Let's walk through this. All right, so we still have same type of information. New table. I'm gonna work this out a little bit longer. So we said we have 602 cocaine negative, 866 cocaine positive. Can anyone grab a paper? So they had to get volunteers so that they could figure out how good their test was.
course, they did survey information. And then they actually did like blood tests. And they found that they were going, I don't know what they were going for, but they found that people actually lied on their survey. I'd be that surprised by it. But here, after, when you throw out all the survey data and look at blood tests, they have about 59% of the individuals who are testing positive. Right? And we can assume that is what's going to happen in our population. If you look up drug usage, you might be surprised at percentages. So, 41% are not, and we'll go with that. We'll go with that. So, first up is probability we get a positive test. Right? So, we have to be a user. And then we have to test positive. And for this test, we said sensitivity was 92.2, 0.922. Our specificity was 84.4. So the one we needed this, 92.2. We also need our false positive. What was that false positive? 5, 6. All right, so we have our numbers. Plus, and we're not user, and all right, so we can break this down. 0.5 plus. All right, so those are actually two numbers that we're interested in because we want to know that yes, given that we test positive, all right, so we want the 0.544 over the sum of those two numbers. And kind of starting to take some shortcuts here and show that we're looking at the proportion of this relative to the total. So we have 64 plus 8. And then you can actually tell the judge, hey, it's actually going to be a lot less. I mean, that's using these numbers. We say that the number of cocaine users in our population, especially my age category, and what I do, my group, my sample that I'm part of, right, it may be down to 10%. That means chance of positive testing, or the chance that you actually have it, test positive. But if he looks at coding, he says, yeah, I don't buy that. I could probably get like 80% chance users here. That's going to throw things off. All right. Question 2 is what's the probability of not being able to test is positive? How'd you do that?
I did the probability of not having it times the probability of true negative over the probability of positive.
We want to know the probability of not on cocaine if our test is positive. So we have this if our test is going to come up positive. It comes up positive when we're actually on it. It comes up positive when we're actually not on it. So our probabilities is this. No, given that we're actually on it, over the 0.608, which will give us 0.105, which is 1 minus that value. because we basically said we don't have, we're looking at that positive test. And if we have a positive test, we only have two outcomes. We're either a user or we're not a user. Some of those. If I ask, if the test comes back negative, what's the chance that we actually don't have it? Then what we have to do is do our negative. What's the chance that we actually have a negative test? If it comes up negative, we have a true negative. If it comes up negative, we have a false. Works the same. All right. Questions? And let me look at my sheets. Did that one quad test? What's our? All right. Do we need to do any more of these? Think you feel okay? We had two questions on the homework that kind of address that. That was my homework 4, so we'll be able to finish those. What's that? I'll probably make it to Wednesday. Finish it up. Some people emailed their homework for me. Yeah, and as I said, you can run the pregnancy test. Those pregnancy tests right now are, they're good. They're good. And if it comes back positive, it's, as long as it's not user error, comes back positive, it has it's chance that you're actually pregnant. It's like over 90%, over 99%. They're that good. Even the dollar store. All right, so practical applications. Maybe you'll use it, maybe you don't. Could come up with, coronavirus testing. I mean, it has all of this. Now, what we can do is, if you knew what tests they were running, you can actually look at the figures, and they could say it's 100% sensitive, 100% specific. Well, that's just in their group of samples, their group of volunteers. All right, and that assumes an ideal environment. Is it necessarily ideal? No, we don't know who's actually running the samples. We don't know what their skill set is with pipetting, with interpreting results, and so forth. But what you can say is that right now, the positivity rate, so of the tests that are actually being tested for, it's only like, I think 5% positive, 6% positive of those tests. So you can use that as your probability of actually having it to figure out if the test comes back positive, what's the chance that I actually do have it. And there will be some false positives. There are some. Other places to use this is in actual Bayesian statistics. Some of you have probably seen it in phylogenies and so forth, where they've used Bayes methods. Bayesian method is basically in assigning probabilities to our outcomes, right? And that contrasts with what I'll term the frequentist approach. So the frequentist approach kind of looks at our data as kind of being fixed and saying this data that we've collected represents a sample of our population, and then we're going to make inferences about our population itself. Our sampling itself is what's allowed to fluctuate. Because if we repeated our sample, then we're going to get slightly different numbers. But then we recognize that. Bayesian approach, though, isn't necessarily utilizing the probability distributions as a way to say, well, our sample is going to vary. It's using all of our old information to update the probabilities. So here's the deal. We have, let's say, a normal distribution, right? Say 1,000 samples. We did it on our test. And then we're going to draw a random sample of 30 individuals. All right? That random sample should be a normal distribution. And the normal distribution tells us or gives us
how our mean should vary and how our standard deviation should vary. Our assumption with this frequentist says our population is normally distributed. With the Bayesian approach, we don't know what that population is. So with our very first sample, we look at our sample and say, okay, well, this looks to be about a normal distribution. And then when we resample, we say, okay, well, using our information that we've just collected, we assume that our next sample is going to also be a normal distribution. If it is, then that updates what we know about it, and it's going to change our location, central tendency, and our dispersion values. And then with each sampling, we're revising our estimates to say, well, we have a certain amount of confidence or a certain level of belief that our population follows this idea. So instead of saying with a frequentist approach that our population is normally distributed, Bayesian approach would say, well, our population is probably 90% likely that it's normally distributed. And that percentage keeps getting updated, all right? The actual statistics part of it is a little bit more in depth, all right? And how we go about analyzing our data, it's a bit more in depth. And it is going to be beyond our scope of this course. And actually, it's going to be beyond the scope of like a graduate level course too. I think Bayesian statistics is kind of a course in and of itself. And reality is that you probably need a bit more math to get through it. So here's an example. So we've been working with the herpes simplex virus as part of our Bayesian tests and stuff. So we're going to study the prevalence in our population. All right. What we're going to do is take repeated samplings of our population to get prevalence values, and we're looking at the overall prevalence. So what the frequentist approach says that our population has a fixed value, has, let's say, 30% in our population. And then when we take our sample, we're going to bounce around that value. Sometimes we'll get 30, sometimes we'll get 25, sometimes we'll get 35. All right, all depends on what that spread is. And we recognize then that our parameters, those population parameters, are fixed. And it's the statistics, our statistical prevalence that we calculated from our sample. Those are the values that are going to change. If we took our Bayesian approach to that, we say that our data, our samples, are actually the ones that are fixed. Those are real data. And then what we're trying to do is assign some confidence level to our estimate of the population. And the population are all unknown. And the population parameters are those that are going to follow then some sort of probability distribution. All right, two kind of different ideas, different realizations of that overall question of, are things different? All right, so is one better than the other? Is the frequentist approach better than the Bayesian approach, or vice versa? It depends on who you ask. It depends on who you ask. It depends on your applications too, right? So for just everyday stats, like what we're going to be analyzing here in this class, frequentist approach works. All right? For anything that you're going to probably do here in a research course, frequentist approach probably works, with the exception of making phylogenetic trees, and then you can do your Bayesian bootstrap methods and so forth. All right, but if you're measuring something and looking at do groups differ, use the frequentist approach. Are you going to get different answers? No, probably not. But doing the Bayesian is going to be a lot more difficult, a lot more computationally expensive, and I always take the approach is always take the simplest approach to do stuff. Questions? Yes? No? All right. That is going to wrap up our introduction to probability. We're not quite done yet. Because what we're going to introduce you to are probability distributions. All right, so we've introduced the concept of probability. All right, using the addition rule, multiplication rule, using those rules to do this Bayesian equations, figure out likelihood that you have a condition if you test positive. Where we're going is using that information to start building these probability distributions, because it's these distributions that give us our expected values, our expected numbers, that we then compare to the observed values. So we're going to start with discrete random variables. Why discrete random variables? Because they're probably easier to conceptualize. All right, they're easier to conceptualize because these are discrete data. What does discrete data mean? What is a discrete variable? It's a whole number, right? It's a whole number. So there is no halves. There are no quarters. Right? It's a whole number. All right, so we're going to introduce the binomial distribution. Well, you've already seen this. All right. Binomial distribution is named because you have two outcomes, binomial. Right? It's also been called the Bernoulli trial. All right, so we have now two outcomes, success or failure, male or female, right? Infected, uninfected. If we're interested in, with this binomial distribution, is try to model the probability that we'd get k successes in n tries. That's what we're interested in. What's the probability that we would get k successes in n tries when the probability of a success in one try is equal to p? All right, so we have a baseline probability. All right, and then we're going to say, we're going to repeat this numerous times. How many successes do we actually have? That is completely modeled with the binomial distribution. So here's an example. It's fish parasites. Right? 10% of our fish are going to be infected with the parasite. If we sample 3 fish, then we want to know what's the probability of getting 0 infected fish, what's the probability of getting 1 infected fish, 2 infected fish, or 3 infected fish. All right? With a small sample like this, we can use brute force, which is basically calculate it manually. All right? So how do we do that? How do we do that? Well, we just basically have to count up the number of ways that we can get it. Let's make sure I zoomed in here. All right? It is super dark. That's better. All right, so we're going to use y and n. So yes is infected, no is uninfected. All right, so we want 0 out of 3. 0 of 3. And the only way to get that is to have each fish get no's. No, 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 right? But we already said the probability of being infected is 0.1. All right, so this is just simply 0.9 times 0.9 times 0.9, right? Probability of 3 of 3 can only happen if we have all 3 fish being infected, right? So all of them, that first one has to be infected. The second one has to be infected. The third one has to be infected, all right? So I've got 0.9 cubed and 0.1 cubed. All right? And we can calculate it on our calculator if we wanted to. That's fine. Get back just a little bit. Yes. All right, what about 1 of 3? Probability of getting 1 of 3. We can have the first one be infected and then the next 2 not. We can have the second one being infected, or we can have the last one being infected. So note, there's 3 different ways now in which we can get this. All right? We still calculate it in much the same way. We have 1 fish is infected, and then the other 2 are not. Okay. actually, I'd probably do this. 0.1 and 0.9. I'm going to use squared, simplified a bit, because we have 0.9 times 0.9. And then this next one, we have 0.9 times 0.1 times 0.9, which gives us basically the same thing. And then we have 0.9, 0.9, and 0.1, which again gives us the same thing. All right, so you can see that we have 0.1 times 0.9 squared. What do we do with those? Well, we can get it in any order. All right, so what we would do is add them all up, or get 3 times 0.1, one time it happens, is 0.9, 2 times it happens. All right, so we kind of broke it down. Our last one, 2 of 3. Now the numbers flip. So instead of no, no, and yes, now we have yes, yes, and no. And hopefully if you kind of look here, it's going to be the same pattern, right? But this time, instead of 0.1 times 0.9 squared, we're going to have 2 of these 0.1s. So, and there's going to be 3 total. So it'll be 0.1 squared so we'd have 0.13 times 0.1 squared times 0.9. So we have all of them. So if we ask the probability of 0 out of 3 fish, it's right there. 0.9. 3 out of 3 fish, 0.1. 1 out of 3 fish, 3 times 0.1 times 0.9. And then 2 out of 3, it's 3 times 0.1 squared 0 times 0.9. So that 3 in the front kind of added up the number of combinations that we have. 0.1 was the probability of being infected, right? 0.9 is the probability of not being infected. And then these exponents correspond to the number that must be infected, the number of successes, and then also the number of failures. So this ultimately comes down to, if you notice a pattern here, we have yes and no. It comes down to our pattern of saying, if we have k of k successes and n tries, all right, we have this equation where we're going to have to figure out the number of combinations that we have that can occur, and then we're going to multiply it by our probability of success raised to the number of successes we have to have times the number of failures that we have, so 1 minus p, times, or raised to the number of failures, so n minus k. And this is going to be a pattern. Almost. We've got shadows. Awful. There it is. K of n is the number of combos times probability of success raised to the k. That's how many successes we have to have. And then 1 minus p raised to the n minus k. That's the number of failures. All right? That's exactly what this is. This is our equation. And what we're going to do is talk about this in lab. So our number of combos is given by list notation. It's a choose type of notation. Have your calculator in lab. I'll show you how to calculate it, how to do this on our calculator. There's a pretty nifty button on there, scientific calculator. I think we can look at Windows calculator too. I believe it's on there if we expand it. But this is our binomial distribution. So what we'll do is we'll pick this up in lab. I think I have some extra probability problems to give you a little bit more practice doing the Bayes or doing any of these probabilities. I'll look. I think it may be part of like the exam prep. So if it is, I might just hold off on that until next week. I think our next exam's in 2 weeks from today, I think. Possibly. All right. See you at 2.